Hi everybody, we're going to start our series for Chapter 5. Chapter 5, as you should already know, is about what we call z-scores, which is a type of a standard score. So we're going to find that what we're ultimately doing is combining a lot of what we learned in Chapters 3 and 4 together into this content for Chapter 5. So let's start by defining this term standard score. A z-score is one type of a standard score. If you think about times in your life you've taken a standardized test, that could really mean kind of one of two things, usually both things. Part of it, a test being standardized, means that how it's administered is the same for everybody, so everyone takes the same questions, worded in the same way, in the same order, in the same circumstances, as part of a standardized test. But the other part of what we mean often when we say a test has been standardized is that the scores are standard scores. So what that means is a standard score is a type of a score or distribution of scores that have a predetermined mean and standard deviation. Again, a standard score is a type of score that has a predetermined mean and a predetermined standard deviation. We already know what the mean and the standard deviation are going to be. Now that should sound probably a little bit bizarre, because how could we go out and take a bunch of measurements without knowing what they are already and already have determined what the mean and standard deviation will be? Well, we'll get to that into this chapter, how we do that. It's a conversion process to make that happen. And so what it really means is that we're going to take our raw scores and we're going to convert them into a set of scores where we know what the mean and standard deviation will be. It's a transformation. But it's not about really changing the data, it's just changing the scale we're using to measure things. If you measured something in inches and then later decided you wanted to convert it to centimeters, you would do a little mathematical conversion, but the thing you've measured isn't going to end up longer or shorter. It's still whatever it is. We're just going to convert to a different scale to describe it. Or if you were measuring the temperature in centigrade and you want to convert it to Fahrenheit, well, you do a little mathematical transformation. The temperature didn't go up or down in the place you've measured it. We're just changing it from one scale to another. So what we're going to see is we're going to often take data, typically raw score sorts of data, and do like this transformation, this conversion process to turn it into a different scale. And these scales are standard scores. So just one quick example that we'll use a lot as an example in this course. IQ tests, pretty much all IQ tests, not entirely all, but most of them have a mean of 100 and a standard deviation of 15 points. And so it almost doesn't matter what IQ test it is, whether it's from the Wechsler scale or the Stanford-Binet scales, or it's from some other a brand, if you will, of intelligence test. They've all been converted into Celsius or Fahrenheit, if you will. They've all been converted into the same scale. So they all have the same mean and they all have the same standard deviation. So why would we do this? There are two reasons why we would maybe want to take our raw scores and turn them into z-scores, again, a particular type of standard score. The first reason is that taking your raw score and converting it into a z-score is going to be able to tell us the exact location of a score within the distribution. So think about things we've been talking about particularly back in Chapter 4, when we're asking, well, would this score relative to the rest of the class, say an exam score, would that be a typical common score, or would it be above the average bear or below the average bear? That sort of a thing. Z-score builds all that in there. I often call it one-stop shopping. We're going to be able to, in one score, be able to tell you exactly how that score stands up, where it is in the distribution, in the middle, the right, the left, its exact address. The second reason why we might use z-scores is that we might transform the entire distribution. So again, this is a bit what I was describing earlier. If I took if I'm developing my own IQ test, and I go out and I give it to a bunch of people, well, I'm going to get a bunch of raw scores from them, but then I'm going to convert them to another scale. Typically we do that for a couple of reasons. One is often we want a scale that's easy to use, easy to relate to. But the other thing is that it helps to make comparisons between two or more distributions easier. So it's about making comparisons, the second purpose in the end. So if I have two completely different measurements and I convert them so they're both on the same scale, if you will, if they're both z-scores, then I can more easily compare them and say, oh, well, did the person score better or higher on this versus that performance metric, for this test versus that test. So it's a way of making things easily comparable. So we'll get into all of that as we continue on through this chapter today. Typically, I find the hardest thing for a lot of students to understand is that z-scores aren't that hard to understand. They're pretty straightforward. Most students want to try to find something harder in it than really is there. It's a pretty straightforward process. So let's stop and think about this idea of what we're doing here again with the z-scores. It's going to help us to, let's think about particularly, we're going to start with that first purpose, to tell us the exact location of a raw score within its distribution. Well, let's suppose for a minute that there was some measure was taken and you got a raw score of 33 points. How'd you do? Is it good? Is it bad? Is it average? There's absolutely no way of knowing, right? There's no context for comparison here. So this is the problem with raw scores. Raw scores all on their own don't tell us anything much. To really be able to evaluate that score, is it a high score, average score, low score, we need some more information. So we talked back in chapter 4, some of the things that might help us to understand that. Well, one of the things that might be useful is if we knew, let's say what the sample mean was, could be sample or population mean. If we knew the mean was, say, 30 points, well, now we know a little bit more. We know that this person scored above the mean, but is a difference of 3 points a big difference or a small difference? We don't really know if it's well above the average range or it's right next to it. What else would we need to know to be able to tell? Standard deviation. So let's say we knew the standard deviation was 10 points. Well, if the standard deviation is 10 points, then we know that about 70% of the scores are going to be 10 points below this 30 from a 20 and 10 points above this 30 to a 40. So we would know that about 70% of all the scores, all the data would be in this range, and a 33 is right there. So in this case, well, that's a pretty typical performance. But what if we change the standard deviation to be only 2 points? Well, now we know that 70% of the scores would be somewhere between 28 and 32. 30 down by 2, 30 up by 2. Well, where is the 33 now? That is outside that common range. So what we get from a z-score, I mentioned earlier, one-stop shopping. In one score, we're going to be able to know all of that. So when we start into the next clip, that's what we're going to see. How do we do that, and how do we evaluate these? We'll see you there.